All right, thank you, Amara. So today we're going to cover the items you see here. First, let's define what mission critical is. We'll briefly review the applicable codes and standards, and then we'll spend the bulk of the presentation focusing on the features of two of the most common types of mission critical facilities, which are data centers and hospitals. We'll cover generator considerations beyond the codes and standards, best practices, and design topologies for each. So there are a couple of key differences between a typical emergency or legally required system from that of mission critical. A basic emergency system is designed to safely evacuate people and prevent hazards by keeping portions of the system operating for a certain period of time. This could be applicable to, say, a high-rise office building. Mission critical, on the other hand, is designed to keep either the entire facility or the critical components of the facility operating for the complete extent of the outage. So as I mentioned earlier, the two major types of mission critical facilities that we'll be focusing on are hospitals and data centers. And both of these types of facilities have either critical data or human lives at stake that must be kept safe during an outage, and they're not able to easily evacuate or be relocated. As with most aspects of building engineering design, there are many code and standards that largely regulate the design and installation of emergency power systems. We could spend the entire presentation going over some of these specific requirements within the codes, but lucky for you, that's not what the presentation is about. The goal is really to dive deeper into the mission critical design, revealing more than the code minimums, but rather best practices. So just to quickly touch on these applicable codes and standards, since they are so important, and you'll know where to go for further research. First off, and probably the most comprehensive, is NFPA 70, which is otherwise referred to as the National Electrical Code. Within this code, there are several applicable articles, including Article 517, 700, 701, 702, and 708. Another pertinent code that is applicable only to healthcare design is NFPA 99, which is the Healthcare Facilities Code. And then we have NFPA 110, which is the standard for emergency and standby power systems. In addition to the codes, there are a myriad of adopted standards which go hand in hand when designing mission critical facilities. FGI is one of them, which is the Facility Guidelines Institute, which is applicable to hospitals and outpatient facilities. Similarly, many jurisdictions have their own state-specific health codes. Just a few of them are listed here, such as California or Florida. Hospital designers must also be aware of Joint Commission and CMS requirements, which are the nation's oldest and largest accrediting and reimbursement bodies in healthcare. And then specific to data centers, there's the Uptime Institute and ANSI TIA 942 standard, which is the telecommunications infrastructure standards for data centers. All right, enough with the boring stuff. I'm going to turn it over to Bart so we can begin to discuss the features of mission critical systems.
Thanks, Dana. In addition to some of the X's and O's, I really wanted to talk about proper planning and processes for design for data centers so that we can set our team up for success. So these first few slides have a lot of words on them. Please bear with me. The first point I wanted to bring up is there are all different types of data centers that have different value sets and different agendas. There's many more, but the four I wanted to point out here today would be a private enterprise data center, usually pretty small to mid-size, from a couple 100 kW all the way up to maybe a few megawatts. In my observation, these are ones where a lot of education to the owner's team is often needed to make sure that everybody's aligned and understands the goals of the project. Oftentimes there's a set budget to build the facility, and future proofing and sort of pay as you go is less important than trying to get to the final build sooner than later. Then we have co-location facilities, infrastructure as a service. These facilities are oftentimes a lot bigger, multi-megawatts to even hyperscale level, oftentimes set up for multi-tenant use that might have different value sets regarding redundancy, capacity, those sorts of things. Hyperscale, a lot of cloud based enterprises use hyperscale, and these are ultra large 20, 40, 100 megawatt facilities. Speed to market, speed to deployment are often big motivators there, and prefabrication of infrastructure is often a solution used there. So their value set is getting the infrastructure down and being able to use the facility as quickly as possible. And then high performance compute facilities. Sometimes these aren't even considered data centers. They just kind of look and smell like a data center. But this is dense kW per cabinet facilities for number crunching. Oftentimes these are not as concerned about redundancy and just really need power and cooling for capacity purposes. And sometimes, they don't even require generators. So you have to understand not every data center is created equal, and you have to tailor your design towards that. Next thing I wanted to talk a little bit about is owner project requirements. So very oftentimes I will see, I would like a tier 2 facility, or I would like a tier 3 facility, or a hybrid tier 3 facility, quoting the Uptime Institute or TIA 942, or a combination of both. And in my opinion, this is a little too vague for what owners need and require. And so creating a simple owner project requirement built on commonly understood vernacular is going to help get them what they need within their budget and create the right investment and meet all of the expectations. So the 4 big buzzwords that we talk about when creating our OPR: resiliency, redundancy, fault tolerance, concurrent maintainability. So, the first one, resiliency, I think a lot of people from time to time would get this mixed up with redundancy. Resiliency is the capacity to recover quickly from a disruption in a nutshell. Redundancy can help you meet the goal of resiliency, but you don't necessarily need it. So you need to understand with your owners what exactly must be up, or what can you bounce back from. And it needs to be a holistic view. You're only as strong as your weakest link. So from network trafficking, shifting that traffic to a different site, maybe there's active, disaster recovery backup sites that don't require you to be as redundant with your electrical infrastructure. Things like continuous cooling for the data center. Whether you're number crunching and you have to have maybe some mechanical units on UPS, or you're going to have thermal runaway, or maybe you can have a little bit of downtime on your mechanical system and let it come back for 3-4 minutes. It's all dependent, and understanding resiliency needs is key to the right design. Redundancy, the inclusion of extra components that are not strictly necessary for operation, but used in the case of failure of other components. Obviously, it's uptime is the first thing that comes to mind, but oftentimes what I'm seeing is it's more used in scheduled maintenance. Being able to de-energize or remove a component from your system for proper preventative maintenance so that you can be proactive on the health of your system. Just saying N+1 or being N+1 on your components may not necessarily alleviate that issue. Based on your value set, OSHA, safety guidelines, these sorts of things, if you can be N+1, still have plenty of single points of failure, and then you haven't met your goals. So one thing that we do, in addition to writing the OPR, is going through a failure mode analysis with your power system, and looking at every single location where, if you remove this component or that distribution path, what happens? Can you tolerate that or not? And by going through that exercise, you'll be able to clearly define what it is you need to do for your owner without simply saying, I want to be tier 3. That could mean a number of things. We also talk about 2 things: capacity component, something like a generator or a UPS or a utility source, as well as distribution component, cabling, cable trays, pipe, duct, cooling lines. Oftentimes people get hung up on the capacity component and neglect the distribution components, which are equally as important in creating a concurrently maintainable high availability data center. Concurrently maintainability, one thing that I think a lot of people misunderstand is that It's to be able to have a capacity or distribution component removed in a planned manner. A lot of people misinterpret that to be an unplanned event. So concurrent maintainability means that if you have a method of procedure, you will go ahead and be able to remove a component and then still keep your uptime. Fault tolerance is for an unplanned manner, whether you have a brownout, blackout, or something, being able to immediately recover automatically from that. And physical compartmentalization is obviously having physically isolated capacity components such that the environment doesn't disrupt any redundancy. And N+1, 2N. These are the things that we talk about when we want to define our OPR. And it doesn't need to be a novel. It can be as simple as a table that are guidelines that will guide you through your design, through your construction, your commissioning, and into your operation. Now I'll transition back to healthcare facilities.
Great. So a healthcare facility, a little bit different, but that is defined as buildings or portions of buildings that include hospitals, nursing homes, limited care facilities, clinics, medical and dental offices, ambulatory care centers, and psychiatric hospitals. However, not all of these facilities are considered mission critical. So here's where the occupancy classification comes into play. A healthcare occupancy is specifically where medical or other treatment is simultaneously administered to 4 or more patients on an inpatient basis. This is where the patients are mostly incapable of self-preservation due to age, physical, or mental disability. So there's an important distinction between a facility and an occupancy that cannot be really interchanged with each other. All healthcare occupancies are considered healthcare facilities. However, not all healthcare facilities are considered healthcare occupancies. For instance, a medical office building can be a medical facility, but under NFPA 101 or the IBC, it would typically be a business occupancy and not required to follow hospital codes. Some of these facility types have no requirements for emergency power whatsoever, so we won't be discussing those ones today. So once deemed a healthcare occupancy, there are further classifications such as nursing homes or a hospital that also have very different requirements. And again, for the purposes of today, we're looking at hospital mission critical facilities. And a hospital by definition is a facility used on a 24-hour basis for the medical, psychiatric, OB, or surgical care of 4 or more inpatients. So now that we've adequately defined, what types of data centers and healthcare facilities we're dealing with, let's move on to the generator considerations for each, beginning with sizing, distribution, redundancy, and engine rating, and then moving on to the overall electrical design, engine airflow, and fuel storage and delivery. When it comes to sizing a generator or a set of generators for a hospital, there are some key differences that can be taken advantage of that other facilities can't. The minimum code requirements for sizing can be found in NFPA 70, Article 517, 31D, as well as NFPA 99, Chapter 6, 7.1.2.7. These codes both state that generators shall have the capacity to meet the actual demand of the facility. Other non-healthcare emergency systems are required to have adequate capacity and rating to support all loads simultaneously. So the distinction here is that this allows you to avoid oversizing generators for a hospital. Historically, a hospital emergency power system will operate at about half of what the code calculated loads will run. So the sizing is permitted to be dependent on any combination of prudent demand factors, historical data, connected loads, or other permitted feeder calculations. However, this is only code minimum, and nowadays providing only a code minimum amount of emergency power in a hospital is simply not enough, especially in a climate like mine in Texas. The codes don't require cooling on emergency power. However, patient care cannot adequately be conducted without the proper cooling. So therefore, similar to the owner's project requirements that Bart touched on for data centers, the same thing handled here in a hospital, where at the onset of the project, you have to decide what may be prudent to put on the emergency power system. Could be cooling loads, could be imaging modalities, or even in some cases, the entire facility. So the way that the emergency distribution is set up for a hospital can also vary widely. The minimum requirements are code-driven, NFPA 70, Article 517, and similarly NFPA 99, Chapter 6, both mandate that the emergency power system is divided into 3 distinct branches using 3 separate transfer switches: the life safety, the critical, and the equipment branches. These 3 branches make up the essential electrical system in any hospital design and are the minimum requirements. Now, we'll mention there is an instance in the code where a hospital does not require to have the 3 branches subdivided by transfer switch. One transfer switch is permitted to serve more than one branch, or all 3 for that matter, but only for systems that are 150 kVA or smaller. So that was code minimum, but again, best practices dictate that the branches are actually further subdivided. This further subdivision allows for better reliability and some redundancy. For instance, subdividing the critical branch into 2 or more transfer switches eliminates a single point of failure and provides redundancy to critical areas such as an operating room. Similarly, you may do the same on the equipment branch and provide redundant feeds to vital equipment, such as the air handling units feeding the operating room. Many elevators these days use regenerative power, so best practices dictate isolating this equipment from other sensitive loads. So you may want to give elevators their own transfer switch. And as discussed earlier, things like cooling systems may warrant their own subdivided branch as an optional branch. Additional best practices that are not code-driven is to provide bypass isolation type transfer switches. These allow for maintenance of the equipment without disrupting the downstream loads. Closed transition switches on critical and life safety are another best practice to avoid those nuisance blips in power during the frequent testing required for hospitals where you're transferring between 2 live sources. The redundancy in the emergency power system is relatively non-existent in the code when it comes to minimum requirements for healthcare. However, best practices would dictate otherwise. The only reference to some sort of redundancy was recently added to the codes in NEC Article 700.3F. And this doesn't necessarily require a redundant engine, but it does state that if the emergency system relies on a single alternate source of power or one generator, the design must include a permanent switching means to connect a portable or a temporary alternate source. So simply providing a tap can connection for a temporary generator satisfies the minimum intent of the code. Best practices, on the other hand, would go above and beyond this. At a minimum, 2 engines should be supplied with some level of redundancy. This can provide a full N+1 engine or partial redundancy with sharing of loads, where in this case, some of the load may be shed if one of the engines goes down. Additional strategies in a hospital design above code minimum is to include an uninterruptible power supply for critical loads, which would ride through any temporary outages while the generators fire up. Or another redundancy approach is to provide a dual utility normal feed to the facility. Additional generator characteristics that the engineer must be familiar with for designing hospitals are the ratings that you find within NFPA 110, Chapter 4, which is specifically the class, the type, and the level. The class defines the minimum time in hours that the system is required to operate at its rated load without being refueled or recharged. Hospitals fall into Class X, which basically means you figure it out. NFPA designates Class X as the time required as determined by the code or the user. So this will vary depending on the jurisdiction, the location, or whether the hospital is in a seismic zone or even specific Joint Commission requirements. Some require on-site fuel to last 96 hours, while others allow there to be on-site for only 24 hours where there's a plan in place to get additional fuel on a preferred contract. And then once we have the class determined, NFPA 110 goes on to define the type of emergency power system. The type defines the maximum time in seconds that the generator must provide power to the load. So a hospital is a type 10, which means the power must be restored within 10 seconds of an outage. NFPA 110 also recognizes just 2 levels for equipment performance. Level 1 systems are where failure of the equipment to perform could result in the loss of human life or serious injury. And level 2 is basically everything else. so where failure or performance is less critical to human life and safety. So as you can imagine, a hospital is a level 1 system. And lastly, when it comes to ratings, the applicable EPA tier ratings also must be understood. The Environmental Protection Agency defines maximum permitted emission levels using tier ratings, which certify that an engine complies. The applicable tier level is determined based on a number of factors: the date of the manufacturer, the usage, the brake horsepower. So this can vary for a hospital depending on the size. So there's really no one size fits all here. And again, the owner's requirements must also be understood. If they're going to use this engine for more than just standby emergency ratings, such as participating in demand response programs, it could affect the required tier rating, which could also drastically affect the cost. So let's jump back over to data centers now, where Bart's going to talk a little bit more.
So I think one key difference with data centers as opposed to hospitals is many of them, the load is almost all optional standby. We're not as encumbered there in those facilities with meeting NEC 700, 701. We're not dealing with elevators sometimes, fire command centers, atriums, and things where codes are dictating what you need to do, and AHJs are upholding that. There's a flexibility and freedom in design, and that opens up a lot of options and possibilities for the designer and the owner. So 3 things I just wanted to touch on today were just overall electrical design with the final build in mind, engine airflow and how critical it is to consider that. People think that generators are all electrical. They're actually more mechanical in many ways. So mechanical engineering is also very critical to the design of a good generator system. And then fuel storage and delivery as well. So for the overall electrical design, we need to start with the end in mind. Oftentimes we'll design with our final build and then peel backwards based on what's needed day one versus the owner's budget. Because one thing where people can run into trouble is if they haven't planned properly for scale. Let's say that you have a paralleled common bus for generators and you'll want to be able to scale that up. And in 5 years from now, it's time to add those next 2 gen sets. The controller technology has upgraded since then. Will that jive with the older generation? Are the owners, operators, and tenants willing to let you test and commission that paralleled common generator system on a live site? Oftentimes that's frowned upon, to say the least. So you need to think about what are the ways that I can expand and scale up my system while maintaining operation. And depending on the type of data center, that may be a huge deal or not. If it's a private enterprise and you want to agree with yourself that you're going to have an elevated risk to go ahead and do this, fantastic. If it's a high performance compute facility that is not going to be negatively impacted with a service level agreement to do that, fantastic. I think co-location facilities, hyperscale facilities are a lot less tolerant to these sorts of things, and great care needs to be taken to think about how you're going to add on to your infrastructure with zero downtime and mitigate risk as much as possible. Secondly, testing and maintenance. Talk a little bit about the tap cans are basically a connection point for either a temporary load bank or possibly a temporary generator or both. If you have a site with 24 generators, it might not make sense to have a tap can for each and have that cost. Or it might not make sense to need to connect temporary cables into generators one at a time to get your testing done. Scale sort of changes the perspective of how you're going to maintain them, what that cost is, and what that schedule looks like. Oftentimes we'll find consolidated systems with a key interlock piece of switchgear that could connect to any generator easily. That could also be used as a redundant bypass means around UPS systems down to the critical load when you're maintaining those. There's a lot of sophistication and a lot of opportunity that goes into the ways in which you can efficiently deploy means to maintain and test your generators. Next would be safety. ERMS, arc flash, things like that. How are your operators going to interact with the system? And you need to understand that on the front end of this during schematic design for those expectations, because if you're talking about remote control panels, manual controls operating from another room, that's real dollars that can add up quickly. And if that's not defined on the front end of this project, budget problems may arise. The other thing is if you've invested in an infrastructure that is fault tolerant and concurrently maintainable, is it appropriate to go ahead and be able to de-energize equipment as needed so that you can maintain it, in which case maybe additional costs for safety features are not warranted if you're going to de-energize anyway. And lastly, what are you looking at? Automation and monitoring. In my experience, people are monitoring just about everything for the data center infrastructure. And we're talking about an EPMS, electrical power monitoring system. In the computer floor, or the white space as we call it, we talk about a DCIM system. You also have your building automation system that you map data points to as well. So there's a lot of data going around, and if that's not clearly defined in your OPR about who's doing what, oftentimes you're going to double dimension that and have either two people pricing up the same scope of work, or worse, neither of them, and you have a scope gap there. So with all of these levels of remote monitoring going on in a data center, you need to be very clear about what points you want to look at and who's going to look at them and who's going to gather those points so that you can appropriately budget for it. Airflow. When you have a packaged outdoor unit by one of the vendors, oftentimes they go through that engineering task to make sure that you have proper airflow across your engine. If you want to have a more hardened facility and have your generators protected indoors, that's the job of the engineer to worry about that. If you have a large generator system and you have 4, 5, 6 or more 3 megawatt engines in the same room, that's a tremendous amount of CFM that you have to deal with. The louver size gets very big, and if that's not understood on the front end of the project, the form factor of the building and the aesthetic are greatly impacted. So we recommend using CFD modeling, computational fluid dynamic modeling, to model the airflow that helps dictate and inform the form factor of your room and how the air is going to be going across those engines from the inlet through the radiator discharge as well. Many a time have we modeled something and found that it was inappropriate and you were going to have a problem with engines overheating. So CFD modeling traditionally was used only for white space cooling, computer floor cooling. We are using it now for generator cooling as well, and we recommend doing that as early as you possibly can in the project because that's going to dictate your architecture. Fuel storage and delivery. Hospitals are in the same boat here, but how many hours of runtime on diesel fuel do you want? What does your bulk storage look like? What does your local storage close to your generator look like? Oftentimes, you have a lot of generators in the same room. There are code limits for gallons of fuel within the room for day tanks, and you need to understand as these generators get larger and larger, up to 4 megawatts each right now, these day tanks can get very sizable, and it becomes a real concern that people need to worry about. The other thing that is outside of sort of electrical design that we have to worry about a lot is the practicality of refilling these generators. A tanker truck can only hold so many gallons. And if you have a large generator fleet and a lot of bulk fuel storage that you need to replenish, if you have 96 hours of uptime or something like that, you need to understand how many trucks do I need, how will they get in and around the site without bottlenecking, how long will it take, and does my service provider actually have the fleet to meet what it is that I need? Fuel capacity and distribution components, in my opinion, are just as integral as the generators, the electrical wiring, and the cooling themselves. This is something that cannot be forgotten about in the design because it's critical to the uptime of the generator. In terms of specifications, generally speaking, I reached out to vendors in the industry and just get a little feedback for what it's worth. The general bullet point from their end was that they're seeing specifications that are a little too long, a little too detailed. I've heard upwards of a 100-page specification for a generator. I think that we can cut down, trim that down, and get down to the core essence of what you're after. I think dictating the way that an indicator light is manufactured is probably excessive. I think telling a generator manufacturer how to build their widgets is unnecessary. I think we need to think about what are the core values and options and expectations we have of our system and allow them to use their tailored and engineered solution to meet the overall core requirements of what we're after. So some things that we see as hiccups that we always try to mitigate is first would be scope responsibility. Again, it's not just an electrical machine. And if it's not packaged and you have it indoors, there's a fair amount of controls and mechanical work that needs to go on as well, as you can see in the picture here on the right. So you really need to have a joint effort with your electrical and your mechanical engineers for how to specify this properly, calculate it properly, and then be clear on your documents about which contractor is doing what bit of work. Another thing that specifications have been vague about in the past is sound requirements. I want a critical silencer. Well, that could mean a number of things. That is a range of decibel attenuation. And honestly, you need to understand what are the requirements of the site regarding how loud it can be from your property line, and then work your way backwards so that you're not either over-designing or doing something that is not in compliance because you're too vague about what you want. Be specific about the decibel range at the distance necessary. Work with an acoustician and your vendors to achieve that goal. Also, heat requirements. I think a lot of people don't understand the real cost implications of misinterpreting the heat rise on alternators as well. Those are real dollars. Those are decisions that may upsize the alternator needlessly, that would either raise the cost of your vendor quotes and or unfairly put someone at a disadvantage. Fire pumps, depending on your authority having jurisdiction, you need to be prepared to understand what are the kinds of breakers that are necessary to do that. And then testing expectations. It's just not for commissioning agents. You need to be very, very clear in the specification of what you expect on the front end for factory acceptance testing, as well as site testing, as well as commissioning assistance. That can be a very large scope or a very minimal scope. You need to be very clear so that you get the best bang for your buck. Back to hospitals.
Yeah, so let's move on to the various design topologies for hospitals. As we discussed earlier, minimums are simply not enough. So the first step is to really define the goals of the project. So the OPR is key. It provides explanation of the ideas, the concepts, and the criteria that are considered to be very important to the owner. This OPR is typically developed by the owner, but sometimes it's developed together with the design engineer, working through all of the options to consider. So decisions are typically made in a hospital with respect to budget, the desired level of redundancy, the desired level of resiliency, as well as future flexibility and scalability. Defining the future growth for facilities or campuses could have drastic impact on the emergency power system design. So it's important to have a good understanding of the client's overall goals when initially working through the design topology. So again, while it might not be best practice, some facilities may only have enough budget for a code minimum design. So this one line depicts the minimum requirements for a hospital. It's basic with a single engine. It provides the code required manual tap can and three separate branches of emergency. So the life safety, the critical, and the equipment. Each branch is provided with a dedicated vertical switchboard section, which is also code requirement, and basically it provides the least cost option. So here's a variation from the code minimum design topology where it adds in just one level of redundancy on the normal power side by adding a secondary utility source connected in a main-time-main switchboard. This dual utility feed may be sized for either full or partial redundancy, but the emergency side of the distribution remains the same code minimum, which is one engine and one manual connection. This is an option that provides for some level of redundancy for minimal cost. However, note that most utility companies will charge some sort of reserve capacity fee to the end user, so this is a consideration when using this type of typology. Continuing to build on the dual utility option, adding a second generator provides a higher level of redundancy. Similarly to the utility, the second engine can be designed with either full or partial redundancy, and the engines are parallel together. So if the second generator is designed for partial redundancy, it may be necessary to shed some load if one of the engines goes down, but this type of typology does not require that manual connection that we talked about previously. And let me just point out, we're using very small scale on this one line. Obviously, some hospitals are bigger, so the load would dictate that you need 2, 3, 4 generators just to handle the load. So just consider, the N+1 as you add on, that is scalable. These are just simplistic topologies for discussion. And continuing to build even further into the reliability of the design, additional topologies will be built by adding on more generators in a main-time-main arrangement, as well as additional transfer switches, like we talked about earlier, that are going to further subdivide the emergency branches. Basically, the number of transfer switches you choose is based on the ultimate reliability and the design, as well as the load considerations that owner is wanting. So there are many different variations of design topologies, all of which are really dependent on the owner's requirements. So a few other things to consider when choosing the best distribution for your design are also location, scalability, fuel source, and of course, cost. The location must be accessible, protected from damage or flood, even if you're in a floodplain, and it may also dictate the level of sound attenuation applied. The scalability of your system may dictate how much space is required up front for future generators to accommodate load variations or expansions over time. There's also variable fuel sources available, including diesel, propane, natural gas. So considerations to the availability of the fuel source, as well as the reliability or on-site capabilities, must be considered for the specification of the generator. So I'll turn it back over to Bart, and we'll finish up with some data center topologies.
Thanks. So my main point is that there's no one-size-fits-all. By going through the process of creating the owner project requirements and going through the step-by-step failure mode analysis and understanding your budget, you will arrive at the right design. So these next ones are common designs. They all have pros, they all have cons. It's about what's best for you. This one, semantics aside, I just call it redundant parallel common bus. This is something you see a lot at hospitals and other facilities. I think the biggest thing that is good about this is it's well understood throughout the industry. A lot of people know how to make this work correctly. And there's no stranded capacity. And by stranded capacity, I mean if something downstream needs to get worked on, the generator can still feed it. It isn't rendered useless like some of these other designs that will show. There are single points of failure, and preventive maintenance can become difficult. Here's a sample. Traditional 2N works well for smaller sites where it's not budget limiting. A lot of easier to PM, but again, if you have to work on some downstream equipment, that generator could be rendered useless and could not serve as a backup to the load. Also, it does not scale well for super large facilities for the simple reason of budget constraints. There are modified versions of that can turn into what I would call a catcher isolated redundant system. All the benefits of 2N, no stranded capacity, but it is more expensive and it is more complex. The ring bus, which we've deployed, is highly flexible, highly redundant, but it can be extremely complex and extremely expensive. So is it worth that investment to have this high availability with multiple sources being able to feed your load at any given time? The failure modes become very complicated and the programming becomes extremely critical. Isolated cache or redundant systems, this is one that oftentimes works very well for very large sites. it scales well, it's repeatable, you can parallel or not. You are reliant on a management control system such that you don't overload your redundant or your catcher system. So there's trade-offs between inefficiency and complexity. With that said, we'll turn it back to Amara to wrap up.